I don't really have a lot of content. I don't know if I have enough time to actually fill the 15 minutes, but we'll see. I'm happy to have any sort of conversation about this topic. I'm going to talk today about this thing called software supply chain security. You probably have heard about it before, and you probably have seen it floating around. And a lot of times when people talk about software supply chain security, they either talk too much about the theoretical side of it, or they talk too much about the practical side of it. And I'm trying to do in this talk is kind of balance the two. So I'm going to actually talk or more tell you stories of when these things go wrong, and when they go wrong, what could happen. And then we'll show you like a quick demo for one possible way of improving your software supply chain security. And right off the bat, before I get started, it's just a very long marketing term that means securing software from where you produce it to where you run it, right? The supply chain is just a term that basically means for us developers CI/CD, right? It's just marketing for CI/CD, right? So, but it also goes into making sure that you are actually using software that you trust, because most developers just download a bunch of random stuff from the internet. So making sure you trust your dependencies, you verify your dependencies, and then securing the entire process by which you get software from where you build it to where you run it. My name is Abdel. I'm a developer advocate at Google. I do this thing called Kubernetes Podcast by Google, and I also work on Kubernetes mostly, anything around containers. And so, I mean, this is what people mean by supply chain. Again, for us, it just means like CI/CD, continuous integration, continuous delivery. You have some code that you write. You take a bunch of dependencies. You put them through a build system. You produce a package, and then you either supply that package to somebody else if you're building a library, or you run that package somewhere, right? I think that this is the simplified version of how a supply chain could look like for most companies, most developers. But one thing that a lot of people actually don't realize is that a lot of our dependencies are actually built the same way. A lot of people today, even open source projects, are using the same exact processes by which you build software and run it to build their own software, except that they don't run it. They just, host it somewhere. They provide you with an artifact. And because of this cyclic dependency between you build your software, and how your dependencies are built, it makes this extremely complex and extremely vulnerable to a lot of types of attacks. And I'm going to talk about some very concrete examples. Just some numbers for reference. Those are research that have been done by Sonatype, Synopsys, and Gartner. These are quite old, but just in 2021, there have been a 650% surge in open source supply chain type attacks. 81% of commercial code has some sort of OSS vulnerabilities. And by 2025, which is next year, about 45% of organizations are going to face some sort of attack of the type supply chain, right? And I'm going to give you some really concrete examples. Some of them are listed here, log4j, remember that one, right? SolarWinds. So let's talk about SolarWinds. That's a very interesting one. So SolarWinds is a company that makes monitoring software. And one of their customers is a company called Continental Pipeline, which is an American conglomerate that supplies the East Coast of America with oil. So they take oil from wherever they produce it in America, and then they just supply to the East Coast, to all the place where the oil is transformed and then distributed. And so SolarWinds was attacked. Somebody at SolarWinds downloaded the package that was vulnerable, patched their own software, distributed the software to their customers. Their customer is one of them is Continental Pipeline, downloaded the software, installed it on their server, and then the vulnerability got activated, and then the attackers did an entire takedown. So they basically locked all the computers, all servers out, right? And the interesting thing with this kind of attacks that we are seeing today is that they have real-world, concrete effects on humans. It used to be that security is something that is fought on the internet. Bad people, good people, trying to fight each other on the internet. When SolarWinds happened, there was 2 to 3 hours queues at gas stations in America because people were afraid there would be no more gas. People were actually scared they cannot buy petrol anymore. And so people were rushing to go to gas stations to stock on gas. So it's something that we will feel as humans. The oldest, I'm going to talk about another story and then come back to one that happened in Sweden 2 years ago. The first time I heard about supply chain type of attacks was, I think you probably, have anybody heard of a company called Maersk? You have probably at least seen it once or twice, yeah, a few of you, right? Yes. So it's a container company. It's a Danish company, and they basically transport containers. And there is actually an article on The Verge, which I highly recommend you read it, because 4 years ago, they were attacked. And the way they were attacked is that somebody put a backdoor in a piece of software that was installed by a Maersk employee in Ukraine. And that backdoor is a worm that basically just, once it was activated inside somebody's computer, it just traveled inside the entire network of Maersk. And one of the things that Maersk did not do at the time is that they did not have network segmentation. So their prod and corporate network were on the same place, right? They had no firewalls, no limitations. So the worm spread across the entire network and just locked everyone out of their computers. Everyone. Servers, computers, everyone was locked out. And this had a lot of effects. It was estimated that the amount of damage that was done by this attack, which lasted for 2 weeks, was something around the line of $5 billion. There was one of the effects, potential effects. So $5 billion that Maersk lost. This number did not include how much their customers lost, because there was customers that shipped stuff in containers, and there are stuff that needs to be refrigerated, and they were sitting somewhere for 2 weeks, not being refrigerated and not transported. And things go bad, especially if you are shipping fresh stuff, right? Meat, fruits, vegetables. So in one of their biggest ports in the US, they have an automated system that scans the license plate of the trucks and then print out a piece of paper that tells the truck where to go park so that they can offload the container. That was not working, and there was about 3 kilometers of lines of trucks outside the port just waiting, right? So these are actually effects that happens in real life. And the funny story, because I think it's funny, how did they manage to recover? They actually found out that they had, so they use Active Directory, or they use Active Directory at the time, and they had a typical Active Directory farm, right? You have a main server, and then you have replicas. One of their data centers in South Africa went down, so got disconnected from the rest of the network just before the attack happened. So they had a fresh copy of Active Directory on a server in South Africa. And they had to ship a hard drive from South Africa all the way to Denmark through the UK to be able to restore, because when the worm spread in the network, even backups got deleted. So like they lost everything. So just like concrete, real life things. Another one, which happened in Sweden just recently, is we have a big company, a big supermarket chain called Coop, right? And 2 years ago, they were attacked, and they were down for anywhere between 24 hours and 6 days. And it was a supply chain type attack through a piece of software called Kaseya, which they use. So it's a commercial software, so they don't build it themselves, they just buy it. And so that's basically locked them out of all the cashiers and the self-checkout booths across the stores, across the entire country. The problem when this happened is that in some parts of Sweden, Coop is the only supermarket that exists there. Like in a lot of very remote locations, Coop is actually known for not operating very big stores. They operate a lot of very small stores. That's why they have 700 of them. 700 is a lot. Sweden is not a very big country. There's like 10 million people. But in some remote locations, that's the only supermarket where you can buy food. And imagine you cannot buy food for 6 days. So why is this a problem? Well, because we build software in a very complex way these days, right? It's extremely complex. And because it's complex, those supply chain can be vulnerable to a lot of types of attacks. The most common vulnerability is a vulnerable package, whether it's intentional or not intentional. Actually, I can give you another example very quickly, the recent one. Do you remember XZ, the SSH one? So XZ is a compression library that is used in SSH. So when you use SSH or specifically SCP to copy files between servers, they get compressed. And there was people that intentionally added a backdoor to the library called XZ, which then is used by SSH, and it was discovered by somebody at Microsoft, because they discovered that once they run SCP to run files, SSH command consumes a lot of CPU, and that's because in the back, it just shipping whatever you're copying across 2 servers, it's sending them somewhere else, right? So vulnerable package, intentional or not intentional, right? That could happen. I mean, not intentional because all developers are good, but also all developers can be bad, and people build bad code, right? You can have a vulnerable package that doesn't look vulnerable. You scan it, you look at it, You read it, you use your scanning software, it looks all good. Once you put it in production, it will download, trigger a malicious update. So it has a built-in mechanism by which it downloads a remote, bash script or something, and then it becomes vulnerable. But when you scan it initially, it's not. And this is actually a very hard kind of thing to detect, because a lot of times when people implement backdoors in packages through this way, they will just base64 encode the URL. So for you, it just looks like a random string, and you wouldn't know that it's an URL, right? So you have to take that URL and base64 decode it to figure out where it is, right? You can have vulnerable source code, right? I mean, again, bad developers exist everywhere, and people write bad code. Or you can have clean code, clean packages, and then your pipelines get breached, right? And this happened actually to a company called Circle CI. This is a managed CI company. They basically got breached, and they leaked their own AWS keys, not their customer AWS keys, their infrastructure AWS keys to GitHub, right? And took them 2 weeks to realize that. So all the combination of these two things can make it a way that you end up with a vulnerable software, right? So I talked about the XZ outbreak. This actually was very fascinating. I highly recommend you go look into the analysis of what happened, because the people who implemented this vulnerability, they were intentionally doing it. Like, it was intentional, it was not, and it took them 3 years to be able to do it, because they started by creating GitHub profiles and contributed to XZ, and they looked like legitimate contributors. And they just kept contributing up to the point where they just added the vulnerability that they were planning to add. It took them 3 years, right? Also, because the funny thing is when you are maintaining open source software, you probably don't know who you are working with, right? Like the people that you just basically saw a pull request, and you just review pull requests, but you don't know the people behind it. You don't know them, you probably have never seen them, and you probably would never see them in your life, right? And a lot of open source, I think there was like I was at one of the Linux Foundation events, and there was an analysis they did on a lot of these open source projects like Kubernetes and the Linux kernel, and a lot of Git itself, and a lot of, and it's like something like 60% of the contributions are called drive-by contribution. So a drive-by contribution is a person that contributes only once. So they would only open a pull request once in the entire life of that project. That's why they call it drive-by, because you just contribute once and never do it again, right? So because your supply chain is so complex, it can be subject to a lot of types of attacks, right? Bad code, compromised source code, compromised build system, compromised packaging system. One very concrete example that happens a lot for us is a lot of times people in production, they don't actually filter out egress traffic. So you have an app in production which makes outbound calls to an external endpoint, but you don't filter that traffic. So you don't really know what the app is doing, right? Or you don't intentionally do it. And you end up with basically a package that once it runs in your production, it will download an extra update that will make it vulnerable, right? So you started with something that you scan that looks good, but then once you run it in production, it just downloads some random updates from the internet, right? So how do we solve this, right? So there have been two basically type of efforts that the security community have been working on. One of them is called Zero Trust, and the other one is called Shift Left. Neither of those are very specific to security. Zero Trust is a networking term, which basically means in a microservices environment, Zero Trust means that every single microservice verifies every single call, and you don't blindly trust that whoever is making a call toward your microservice is a legitimate actor, right? So you have a way to verify that call, whether you typically authenticate. And shift left essentially is a word that we came from DevOps, which meant which in the context of software supply chain security, it means making developers more aware of what they're doing. Not necessarily shifting the responsibility to developers, but just making them aware of what they're doing. And I'm going to talk a little bit, I'm going to show you some concrete examples about the Zero Trust part. So a few years ago, there was this project that got started. This is a community project called sigstore. So sigstore is a combination of multiple companies. All these companies are contributing into sigstore. The main driver is a foundation called OpenSSF, which stands for the Open Source Security Foundation, which is a sub-foundation of the Linux Foundation, and they are doing actually security for open source, generally speaking, right? And then there is a bunch of other companies. And so they do three main things. they build software to sign and verify other software, and then they have ways to monitor whether software have been signed or not. And I'm going to show you concrete examples. So one of the frameworks that sigstore works on is a framework called Salsa. There is an A missing, but we still pronounce it Salsa. And it stands for Security Levels of Software Artifacts. And essentially, Salsa is a checklist type framework that has a set of requirements that if the way you manage software and the way you build and ship your software meets all these requirements, you can say that my supply chain is level 1, level 2, level 3, or level 4 compliant. The checklist looks like this. It's a very complex, long checklist. This is the first version. There was an update to Salsa framework that focused only on the build. But we can quickly look at Salsa 3. You see the column that says Salsa 3. And on the left side, it says, for example, that you have version source control, verified history, retained history for 18 months. You have a scripted build system. You have an ephemeral build system, which basically means you don't run 2 builds in the same environments, blah, 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 blah. So those are all requirements, right? And if your software meets those requirements, if your supply chain meets the requirements, it basically means you're compliant with one of the levels, 1, 2, 3, or 4. There are 2 big projects that are actually already certified to be Salsa 3 compliant, and you probably know them, Prometheus and Argo. So Prometheus and Argo have all been through the certification process, which there are companies that does this for money, of course. You can do it yourself. One of them is ChainGuard. It's a company that does this. I'm not affiliated with the ChainGuard. I just think that they're doing cool stuff. And so the other thing that they do is that they build also software and tools. And I'm going to show you today cosign, which is a tool to sign and verify containers, right? Or OCI images, technically. So any image which is compliant with the OCI format, you can just verify it with cosign. But they have a bunch of other things. One of my favorites is a tool called Recore. So Recore is a public ledger where you can find traces that a piece of artifact have been signed. So you can actually go there and search for a library, and then you can see if that library have been signed, who signed it, when it was signed, and all that stuff, right? Just a public ledger. They also have like a public key infrastructure, because in order to sign stuff, you need certificates and keys and stuff like that. So they have a bunch of infrastructure that they offer for open source projects for free to be able to implement all these mechanisms. But the whole point of the Salsa framework is to do this, or the whole point of the sigstore framework is to do this. On the left side, you are the developer. You are building some sort of software or artifact. You have the artifact. Before you publish it, you go request a certificate. So you can get certificates from anywhere you can get certificates from, but they have their own service called Felucio. So Felucio is just a certificate authority, right? You download a certificate from Felucio. You use the certificate to sign your artifact, which is on the top right corner, signed artifact. Then you publish that into Recore, the transparency log here. Once you publish it, any end user can basically go into Recore, type the name of your library, and then verify if that library have been signed, who signed it, who issued the certificate, and all that stuff. So this is supply chain security according to sigstore. This is their version of supply chain security. But you don't have to do this, because this is mostly for open source stuff. The idea is that you can get inspired from all these processes and implement them even privately. Of course, privately, you're not going to use a public certificate authority. You're not going to have a public Recore because your libraries are private. Recore is both a transparency log, but also a piece of software, so you can run it yourself. You can have an internal version of Recore, right? And I know there is actually, Maven is working on a Recore-specific instance for Maven. So very soon there will be a Maven Recore, which you can look for Java libraries, and then you can see who signed them, how they were signed, and all that stuff, right? We talked about Salsa. We talked about the levels very quickly. The last piece of the puzzle for supply chain security is this thing we called SBOM, and which stands for Software Bill of Material. I have a very, and I will go back to the previous thing because I forgot to say something there, but I have a very basic, very dumb way to explain what SBOM is. You can think about SBOM as being the recipe version of your grandmother's favorite recipe. Whatever recipe your grandmother used to cook for you and left you with a recipe, that recipe is a set of instructions and a set of ingredients, right? For software, the ingredients are the libraries. So SBOM is the list of ingredients. The only difference between a recipe and software is that your grandmother's favorite patata alla riojana, maybe, right? Yeah. That's basically a list of ingredients that you can just buy over and over again and replicate the dish multiple times. in the context of software, each artifact will be different because artifacts are not built the same. So each SBOM should be unique to that specific artifact. And if the artifact changes, the SBOM should change. Make sense? So going back here just really quickly. This, another dumb way of explaining all of this to people is to say, you know when you go on the internet and download the command line, and sometimes with that command line, there is a SHA-256 file, right, that we all download and we all verify, right? We all do it, right? Good, okay. So that SHA-256 is the signature of that command line. So the people who publish the command line, they will calculate the signature, and then they will publish the signature in a text file called .SHA-256. And what you're supposed to do, you're supposed to download the CLI, download the SHA-256, and use a command line on your computer to verify if the signature of the command line you downloaded matches the published signature, right? This is just a more fancy way to do it. It's exactly the same thing. This uses certificates and public keys and private keys. The SHA-256 example uses a very simple checksum command. Make sense? So the whole point of this is we don't have to do SHA-256 anymore because it has its own set of problems. Then this is just a more sophisticated way of doing it. Make sense? Good. So putting all these things together, using SALSA or SBOM together or separately are supposed to be complementary. You can use SALSA itself, you can use SBOM, you can use both, you can use none of them. SBOM, by the way, is going to be mandatory in Europe starting 2025 because the European Union have published a law called NIST2, N-I-S-T2, which forces companies operating in certain domains to generate, store, and supply SBOM if they're asked by the regulators. And that's the new version of GDPR, right, that the EU introduced. And companies in which sector you might ask, finance, healthcare, energy, blah, 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 the key ones. Military, of course, you know, the major sectors. The sectors that if something goes wrong, people's life gets impacted, right? So let me show you a very quick example of how this looks like. So I have a very simple app here, which is written in Go. So it's just a very simple application, which has a Docker file. And I'm going to use that to build my application. OK, I'm going to not do that, and then just go copy the command directly to build this application. So it's a very simple hello world. I don't really care too much about what it does. I just care about showing you an example. So I'm going to build it. I'm going to wait for a second here. And I'm going to show you the example I'm going to show is using Kubernetes. And if you don't know anything about Kubernetes, just know this very, very, very basic, simple fact. Kubernetes is a super stupid system when it comes into deployment stuff. When you tell Kubernetes, please deploy this image for me, as long as it can pull the image, it will download it. It doesn't care. That image could be coming from your own artifact registry, or it could be coming from Docker Hub, or it could be coming from iwillhackyou.com/good image, trust me, right? It will run it, right? So I built this image. So I'm a developer, build the image. So far, so good, right? So if I do this, my image is there. Now what I'm going to do, I'm going to tag it because I will push it to a remote container registry. Don't worry too much about what these two command line means. It's basically just tagged the same image with two different tags, one called unsigned and one called signed, and I will explain to you why later. I will take my unsigned image, and I'm going to push it to a remote container registry. So Docker push will push my command, my container to a remote container registry, and it will fetch the SHA, the unsigned SHA, the signature. It will fetch that, right? So if I do echo on $this, then I have my unsigned SHA there, right? Cool. So I'm going to go into, I have a Kubernetes cluster, and I'm going to deploy this container image on it without doing too much to it. Just give me 1 second. OK, cool. So again, don't worry too much if you don't understand what this command line means. I can explain to you. It basically just creates an application inside Kubernetes called unsigned-hello world, and it's pass an image, and the image is my unsigned image, okay? So this is just to demonstrate the fact, the very simple fact that Kubernetes world, as long as the image is downloadable, it's installable, right? So basically what I did is what most people do. Build an image, push it somewhere, deploy it. No trust, no verification, nothing. Of course, this is stupid because no one can tell me, no one actually can ensure that that image is coming from me. I could have downloaded this from the internet. I could have literally Docker pulled it from, again, iamahacker.com to trust me this is a good image, right? Kind of thing. And would run it on Kubernetes, and that should be a problem. But that's actually a problem in the sense that I just run a bunch of untrusted code in a cluster, right? So how do we avoid to do these problems? One of the ways you could do it is you could use a command line called cosign. I'm going to show you. So I'm taking my signed image this time, and I'm going to push my signed image to my container registry and fetch the SHA. And then I will take this cosign. So cosign is a command line tool that is published by sigstore. It's cloud agnostic in the sense that as long as your container image is OCI compliant, OCI stands for Open Container Initiative, and that's the spec that all container tools use to build images. That's basically the standard spec. That's actually what allows you, for example, as a developer, to use Docker to build an image and use Podman to run it, because they both just implement the OCI spec, right? So as long as your image is OCI compliant, as long as it's in a registry that cosign can talk to, and as long as the key is either coming from a KMS, a key management system, or it's a key that you generate yourself, right? In my particular case, you see on this line number 52, where it says -- key, I am passing a key which is in GCP KMS, so that's Google Cloud Platform, our version of key management system, which is just a tool that generates and stores keys, right? So public and private key. So the key that you have there after the flag -- key, that's just an asymmetric key, a public-private key, right? So now what I did is I will tell cosign to use that key as an input and then sign the image, which is the last line. So cosign sign, blah, 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 blah. So this will take the key. What's going on? Hold on. This is not good. I know why. Sorry, I need to authenticate. And that's not good in the sense that, sorry. Just bear with me 1 second. I am hopefully not going to show you my password because I want not to do that. Let me go fetch that here. And then hopefully I don't end up exposing my password on the recording. And then I'm not also supposed to show you this key, but that's completely fine. And then I need, that's the issue with this thing, is I need to authenticate twice. Sorry, when I was authenticating, I used the wrong project to authenticate, so that's why I had a permission problem. All right, so now it should just work. Continue not to show anything I shouldn't be showing. All good. Okay, boom, and then boom. All right, cool. We should be good to go now. So now if I try to sign my image, it looks like it's working. So what's going to happen is if I go look at the container registry, so this is the Google container registry, this is where I push that image. This is the signed image. If I click on it, I see that there are actually 2 artifacts inside, right? The bottom artifact, which is 3 minutes ago, that's the image itself, right? The top artifact is the actual signature, right? And you can see that I only have 89 vulnerabilities, so it's not too bad. So if I go into the top artifact and I go into the manifest, I will see that there is a signature. Do you see the last line in the JSON payload? That's the signature. That's the unique signature of that container image using the public key coming from KMS, right? So now theoretically, if I give this image to anyone and I give them my public key, they can just verify it, right? So this is exactly what I'm going to do now. I'm just using cosign again, using the same exact parameters, except that as an input, as a command now, I say cosign verify, using the same key, same image. I run it, and this should say the cosign claim were validated, the signature was verified against a specific public key. So what I did right now, I just established trust. I built an image, I signed it, and then verified it. Of course, in a real world scenario, you will be developer building and signing, and somebody down the line, through the supply chain, will verify that image. Whether it's a person that wants to trust or verify that that image is coming from you, or a CI/CD system, or whatever supply chain thing you're doing. Make sense? Of course, if you're curious, because I am a Linux geek, if the signature was verified properly, the exit code will be 0, right? So that's essentially how you would, in your CI scripting, say, okay, I ran the verify command, but how do I make sure that verification worked? Well, you just look at the exit code. If it didn't work, it will be exit code 1. Make sense? Good. Now, how do I take this further? Well, luckily, those cosign people, actually, there is also another demo I could do, but I'm not going to do it. You could generate an SBOM. So there are multiple ways you could generate SBOMs. Docker has a feature to generate SBOM. There are a bunch of other tools. I use this tool called Syft, S-Y-F-T. So you can generate an SBOM, you can attach it, and you can also sign the SBOM itself. If you want to take the verification even further, you can sign the image, attach the SBOM, and sign the SBOM. So you have both ways to verify that the image was signed by the people who said they signed it, and the SBOM itself was also signed by the people who said they signed it. Right? I'm not going to show you that. I'm going to skip through this. So in Kubernetes world, there is this concept called admission policies or policy controllers. And so in Kubernetes, a policy controller is a piece of software that registers itself with the control plane and tells the control plane, whenever these actions have to happen, verify with me first, and I will tell you if you're allowed to do it or not, right? This is called an admission controller in Kubernetes world. So cosign, they created an admission controller that basically allows you to deploy a policy in a cluster and say, for these images, verify the signature against this key. And if the signature is not verified, then that will not be allowed to deploy. So I already deployed the policy controller. I already created this policy, and you can see in the policy I say I want to apply the policy to all the images. That's the glob star star, so all the images. And then I want to verify the signature against this key. This is the same exact key I've been using, right? And so now what I can do, so for cosign policy controllers to work, I need to also do an extra step, which is I need to tag in namespace. So I need to put a label on the namespace which says policy.sigstore.dev/include through. And that just allows you to basically, in a cluster, to enforce policies differently. So you can have one namespace, dev, where you don't enforce policies, but you don't care, but you want your production namespace to have policies enforced, right? So once I have labeled my namespace, then what I can do is I can go back to my initial example, which is when I deployed the unsigned image, you remember? So I will take that unsigned image, which is here. I'm going to copy it, and I'm going to go and attempt to deploy it in this namespace. So remember, the namespace is the one where the policy controller is deployed and is set to enforce policies, right? So if I take this, hold on. No, but I need the SHA. Oh yeah, there we go. So if I take this unsigned image that I have here and try to deploy it, that should just fail. Sorry. So this should just fail, and it will fail by telling me that no signature have been matched because the container image is not signed. But now if I want to deploy my actually signed image, then it should just work because it's been signed, and then the policy controller will verify the signature against the key, right? Make sense? So it's just a very simple way to basically build images, sign them, verify the trust, verify that they have been signed, and then also enforce that you don't allow stuff to be deployed in your cluster if they haven't been signed. So this stuff only works with Kubernetes. Cosign works with anything container image, but there are equivalent tools across all type of different various ways deployments for VMs and for other kind of environments. And that's it. That's all I have for the talk. I think I am at 35 minutes, more or less. So I'm happy to answer any questions. Thank you very much. Yes, well, one of you.
normal use of signing and validating the signs we used to share with third parties. I mean, would you do it in your own systems as well, just in case if you were managing multi-cloud or stuff and sharing images from one side to the other?
Yeah, you just share the image and the public key.
Yeah, I mean, in your own, environment. I mean, you're not sharing with third parties.
Oh yeah, of course. I mean, this stuff would apply to even in your environment, even if you're not like working publicly, even privately, because you still want to make sure that the images are coming from your actual developers, right?
Someone is.
Yes, because one very simple example that I think of, the problem I have with this example is I don't have any example to actually demonstrate that this happens in real life, but it might. If somebody steals your developer laptop, right? If somebody steals a laptop from a developer in your company and somehow have access to their password, or maybe cut their finger to unlock with the Touch ID on Mac, then they have access to their internal tools. And since everybody these days works with Git, basically all your intellectual property code is copied in all the developers' hard drives, right? So somebody could potentially try to hurt you by pushing a bad change. That could happen. I mean, theoretically it could happen. I don't know if it actually happens. Yeah. So yeah, I mean, yes, I would do it even internally. Yes, to answer your question, yes. Yeah. And then if you are working in the public, working across multiple companies, just publishing the public keys because the public keys are public and no one cares. And just don't publish the private ones, and then that should just work. Yeah. There was another question?
Cool. So thanks. Thank you for the talk. I think this was very, very interesting. Something that I noticed is that this is kinda putting the burden of actually verifying this on me, me being the developer or the SRE, and we kinda know that doesn't work particularly well. Like, I'm a very lazy person. I will probably not do this. So is there any way or an idea for eventually to be a way for a system to know, is this image supposed to be verified or supposed to be signed, let's say? And if it is supposed to be signed, then I will check and fail if it isn't.
That's a very good question. Well, I think if you are building such a system, which then you will have to build this, right? One easy way you could do that is labels, right? Like you label the images, and then based on the labels, you can verify whether something is supposed to be signed, as you said, or not. That could be one way to do it. I think most cloud providers have some sort of this, but fully managed, so you don't even have to care about it too much. I know we have it on Google Cloud. I know Azure have some stuff like this, where, but the challenge, of course, is that you have to use their product, right? If you're going to use something like a third-party software, like Argo CD or Jenkins or something, then you will have to implement all these extra checks yourself, unfortunately. So I think that to answer your question in a more broader way, the problem or the reason why these things doesn't exist out of the box today is because everybody's requirements are different, right? And depending on your internal security team requirements, these might or might not be a problem. And so then it will be hard for actually companies to provide like a prescriptive out-of-the-box solution that does all these things out of the box, right? So that's why, but I think it's a gap in the market. I think there's probably space for this kind of stuff, especially with this law that I talked about coming in Europe. I think that a lot of companies will be rushing into trying to buy any available solution to manage SBOM. SBOM is a huge problem for a lot of companies. Generating and storing SBOM is a huge problem for a lot of companies. So, but yeah, I don't know if that answers your question.
Yeah, I like the fact that it doesn't exist can answer the question. How to build it is, it's probably
yes. That will depend on what are you trying to achieve.
Yeah.
Yeah.
Thank you.
No worries. Any other questions? All right. Thank you very much. Thank you for having me.